chapter 4.3, we're going to define the separation of variables technique in order to start solving our governing differential equation. When we non-dimensionalized our governing equation, we were left with a partial differential equation that has two terms, one with respect to xi and one with respect to zeta. In order to solve this equation, we need to simplify it. And the separation of variables solution basically assumes that the solution to this differential equation, theta, which is a function of both xi and zeta, can be separated into two functions called capital X and capital Z, each of which is only a function of one variable. So our capital X is going to be only a function of xi, and capital Z is going to be only a function of zeta. And it probably sounds a bit unrealistic to just assume that this kind of solution exists, but physically, a lot of mathematical problems have solutions of this form. This is not the only solution to the Laplace equation, but this separation of variables form is going to be the correct solution for the physical situation we're solving. So that's why we're pursuing this. And I realize that we just non-dimensionalized the equation, so it seems a bit frustrating that we're now going to transform it into an x and a z, but that's exactly what we do. And so to redefine the equation, we want to differentiate theta with respect to xi, and because z only depends on zeta, when you're differentiating with respect to xi, z is just a constant. So it's a constant for the first differential. We differentiate again with respect to xi, and z is still just a constant, so it just sits there. And we have a new expression written in terms of x's and z's for the first term of our governing equation. Now we need to do this for the second term, which has the zeta. So if we differentiate theta with respect to zeta, in this case, capital X is a constant because it only depends on the xi. If we differentiate again, we get the second derivative with respect to zeta. And now we're in the position where we can combine these two transformed expressions into our original governing differential equation. Plugging them in, we get what actually looks like a slightly more complicated form of the governing differential equation. But stay with me, it gets easier. Once we've done this transformation into the variables, the functions x and z, we can actually divide both sides by capital Z and capital X and pull the z and zeta related terms over to one side. And we see that the left-hand side only has terms related to x and xi, and the right-hand side only has terms related to z and zeta. This is actually a huge victory in terms of solving this equation. And we'll just take a graphical look at this. The left-hand side is on the ordinate, the right-hand side is on the abscissa, and because the solution sets these two equal, the solution is going to be somewhere along this one-to-one line. And I'm going to focus on an arbitrary point on this line, and we'll call it value lambda squared, lambda squared. Why did I choose lambda squared? Yeah, we'll get there. So now, if we choose to plot the left-hand side of the equation versus its variable xi, we have to hold the right-hand side of the equation constant. And so we know when the right-hand side of the equation is constant at lambda squared, that the left-hand side of the equation has to equal lambda squared too. So for any variable of xi we choose, that equation, 1 over x d squared x dxc squared, has to equal lambda squared. So another way of looking at this is that the two sides of the equation have to be constant, because you can't vary zeta and not have xi vary as well. So it doesn't mean that there's just one eigenvalue for the problem. There's a range of eigenvalues or values of lambda squared that the problem can take on. It's just that those two sides of the equation have to each equal a constant, and it's the same constant. That is very powerful because it enables us to separate the two equations one from the other. So we can now write all of the x terms in the form of one equation and all of the z terms in the form of another equation. And what's significant here is that we've gone from having two partial derivatives to having two ordinary differential equations. And that's something that we can actually solve. The last thing we're going to do, since we've made this xz transformation for a separation of variable solution, is we're going to rewrite the boundary conditions in terms of x and z. I've copied here our non-dimensional boundary conditions and our expression for theta as a function of x and z. So, to actually rewrite our non-dimensional boundary conditions, we'll plug in theta equals 0 to the first one for x equals 0 and z equals zeta. And what we see is that because theta equals 0, either x of 0 can equal 0 or z of zeta can equal 0. I mean, I suppose you could have the case where both are equal to 0, but only one of them has to be 0 to set theta equal to 0. But it would be incorrect for z of zeta to equal 0 because that would completely remove the z dependence from this problem, and that's aphysical. We know that there is a z dependence of the heat transfer in this problem, so that means we have to choose x of 0 equal to 0 for our boundary condition. Likewise, for these other two boundary conditions with zeros, x of 1 is 0, z of 0 is 0. For the last one, we just plug in the values that we have, and that boundary condition is a little less useful to us. But all of these are correct, and they're transformed, and they are ready to use when we solve for x and z. So that's what we'll do next. Thank you.